So I'm going to demonstrate how to prove the product version of the algebraic limit theorem. So just like all the other ones, we're assuming we're working with convergent sequences, and our goal is to show that the product AN BN converges to AB. So I'm going to start by making sure I know what expression I'm trying to show is small, and by looking at the conclusion, I see that that expression is AN BN minus A times B, and I want that to be less than epsilon. Now I know from my hypotheses that I can control the size of AN minus A. I can make that less than whatever I want. And also same thing for BN minus B. I can also make that less than whatever I want. So what I really need to do is answer the question, how does the absolute value of AN BN minus AB depend on the absolute value of AN minus A and the absolute value of BN minus B. So when I go ahead and I look at the expression AN BN minus AB, I notice that it's nowhere near ready for me to factor out an AN minus A or a BN minus B, because, for example, if I wanted to factor out an AN minus A, I would need to have the same coefficient on AN as the coefficient that's on A, and right now one of them is BN and the other is B. This tells me that I need to change the way my expressions look by adding and subtracting the terms that I need to be there. So AN BN minus AB. I just said that I really would like to have the same number multiplied against AN as the one multiplied against A, for example. And so I'm going to say, well, I've got AN times BN. What I don't have is A times BN. So I'm going to add that back in after I've subtracted by it, and now I'm going to add by it. That's my fancy zero that we talked about in class the other day. And then I still have the minus AB. So all I've done in the middle here is I've added a fancy zero. But it was motivated by what I needed in order to factor out, or isolate AN minus A by itself. So now I can do that if I just focus on these two terms here. That would be BN times AN minus A. And then I still have that other stuff plus, ABN minus A times B. Now, I also want to see how BN minus B might be factored out. And conveniently, this choice that I've made for what I needed to add and subtract for my fancy zero, part of it ended up helping me isolate AN minus A, and the other part is going to help me isolate BN minus B, because now I can factor A out of these two expressions here. And now I have something that allows me to see BN minus B together. I'm going to use the triangle inequality to split this apart. And I am going to then isolate further by bringing the absolute values in around each of the products on my terms. Now, I know that I'm going to be able to make a replacement for AN minus A. I know that's going to be less than whatever I decide to put in my box. And I know I can do the same thing for Bn minus b. So Bn minus b is going to be less than whatever I put in that triangle expression from the convergence of Bn converging to b. But what I'm allowed to put in these boxes has to be a fixed positive real number that doesn't depend on n. And what that tells me is that I currently have issues with this first term because I can't cancel the absolute value of Bn by using my box. Things that depend on n are not allowed to go in the box, which tells me I can't, put in there, for example, I couldn't put epsilon over the absolute value of Bn. That tells me that what I need to do is get rid of that expression Bn and relate it to a single fixed number, because I can only handle fixed numbers inside the box, and we know that Bn converges to b. But what that really tells us also is that Bn is bounded. And that implies that there's some m such that if I look at the absolute value of Bn, it's less than or equal to m for any little n that I pick. The motivation for doing this is because I got to a point where I said, I can't choose what's in my box because it would need to depend on n. So I need to get rid of the part that depends on n, and the way you get rid of the part that depends on n in general is to relate that expression to a constant. When you take a sequence and relate it all to a constant, you're really talking about boundedness. So now I can say that in another step that this is actually less than or equal to m times my box plus absolute value a times my triangle. So now it seems like what I would want to put in here would be epsilon over 2 times m, and then in here I would put epsilon over 2 times absolute value a. Now epsilon over 2 times m is valid because m is positive, so that whole number overall is a positive real number. But the issue that I have here with having absolute value a in the denominator is that what if a equals 0? So now that's telling me I got to do cases. Now if a was 0, this whole term wouldn't even exist. We could go back and restart the problem using a equals 0 everywhere, and what you would see is that this term wouldn't exist, this term wouldn't exist, and you would really only be doing a comparison of this one. And you've already proven this actually as a homework problem. I handed you a Bn that was bounded and an An that converged to 0, and so it's just like the proof of that problem, which I believe was problem 4 on your homework. So proceeding as if we're in the case when a isn't 0, then we know we're gonna choose capital N1 such that for all n greater than or equal to n1, the absolute value of an minus a is less than epsilon over 2m, and we're going to choose n2 such that for all n greater than or equal to n2, Bn minus b is less than epsilon over 2 times absolute value a. Then that means overall I'm going to use the max of n1 and n2, so that, for all n greater than or equal to capital N, I'll then be able to bring down all of this work that I did. So all of this part right here, I would just slide this down and put it down here, and then my final step, and at the end, out would pop epsilon, and that would be my proof. Hope this helps.